With that, Bill, please take it away.
All right, thanks, Zach. So I'm Bill. I'm at Intel now. I'm in Intel Graphics. I work for Theo, who presented earlier. Sort of an applied research thing there. So I run into this stuff all the time. This is a bit more of a sort of informal talk. So thank you all the other presenters for providing your deep technical contributions. This is more a talk, instead of about some sort of deep technical contribution, this is more a talk about, FPBench as a whole and the community as a whole. And so it's loosely, this is just really some musings on the classic David Goldberg paper, which I highly recommend, perusing again. Many of you are probably familiar with it. It's maybe not the best introduction to floating point, but if you're already familiar and an expert, it's a fun thing to read now and again. So this is sort of like my, updated summary. What do I think? What maybe a little bit what's different now, and compared to how we were thinking about floating point back in 1991, which was an astonishingly closer date to when IEEE 754 was published than it is to today. So I'll sort of break this talk into three rough pieces. First, I'll review Goldberg's material with my own sort of very high level presentation. What should everyone already have known before the 21st century about floating point? And then I'll dive into what I'm thinking about, what I think a lot of people are thinking about today, and then what I hope that we're thinking about further on into the future as this community and as our research evolves. So just 10,000 foot view. What is floating point? This is obviously, I'm preaching to the choir. This is going to be a refresher, but hopefully I can make it kind of fun. What would I say to teach somebody new to the area what floating point is, or maybe actually FP stands for finite precision. We don't have to use floating point. Well, the basic problem with representing numbers on a computer is that there are an infinite number of reals. I haven't divided this line. There's just an infinite number of them, even between 0 and 1. But computers are very bad at dealing with continuous things. They deal with finite things. So generally we have to pick some finite representation. Maybe we can distribute them a little bit more cleverly so that we have, a more useful set of represented things. Or since this is the 21st century, we can also do away with the idea of a finite number and just say we have a finite amount of precision per exponent. And we can animate the progress of this thing over the real line. And so, this is great, right? We can represent a subset of the points. This is much easier for a computer. It covers the whole, any magnitude. You can get a certain amount of precision. What could possibly go wrong with this? Well, the answer is basically rounding. Since you have an approximation, there's going to be some error that's introduced. This can happen in all sorts of fun ways. So one of my favorite ways to show this is this very simple interaction that you can have with any Python interpreter you like. Just import math. You can see that pi is an entirely reasonable thing. However, if you do some math, which should, we're adding and subtracting the same number, so we should get pi back, right? Well, yeah, but pi is 4. So this is a very fun interaction that you can easily have if you want to demonstrate catastrophic cancellation. There's all sorts of other interesting things that will happen when you have finite precision. So I can throw up some pictures from my thesis if you're doing some sort of stepwise iterative approximation of a function. If you make the step size smaller, if you take more steps, you'll get more accurate, unless you have a finite amount of precision, in which case you might run into some sort of round off boundary, and then suddenly decreasing your step size, taking more steps, makes you less accurate, strangely. There's lots of sort of interesting behavior like this that you'll see. And so this sort of, what do we do? How should we think about these problems? Again, from sort of 10,000 feet. One of the things that I sort of like to classify here, pardon me, I might be off by an ult or two, but really there's approximately two kinds of numerical problems. There's easy problems and hard problems. If you only have one rounding, this is probably an easy problem, because hopefully whoever implemented the thing that does the rounding implemented it correctly, or at least tells you what the rounding is. And you can easily, you can go look that up, and then you have a tight bound. You can reason about this. You can use this in a proof. Hard problems, however, involve multiple roundings, because as soon as you actually compose operations, as we saw on the previous slide, all you have to do, one addition, IEEE 754 floating point arithmetic pick your favorite precision. One operation is correctly rounded, but two operations, even just two additions, might completely throw away all of the information that you have in those numbers. So as soon as you compose, your operations compose, but your analysis does not. So this is sort of like, if you want to do triage, if you want to understand if your problem is difficult, this is, I think, one of the most basic things to keep in mind. Error does not compose. That's why analysis is challenging. And it's also interesting to realize that there's an interesting, division here between the kinds of problems that exist and the typical people that will be experiencing these problems. Because there's also sort of two, again, I'm off my old kinds of developers, right? There's the people who want to use numbers to compute stuff. They just want to do math. And then there's, a smaller group of people that I think is greatly overrepresented here that are actually, implementing the machinery underneath all of this computation, the sort of library builders. And it's interesting how these different groups interact with these questions differently, right? Users want to ask hard problems because they want their complicated piece of math to be correct. On the other hand, library builders, they're the ones that are responsible for answering the easy problems, which turn out to be very hard. It's not easy to implement a power function that's correctly rounded, even though it is one operation. It's easy to tell a user that it's correctly rounded, and it's easy for them to reason about that. But in a lot of cases, they're not going to care because they're going to be feeding in something from another computation that's already inaccurate, and then they're going to be complaining that the accuracy of their larger computation is wrong. So it's interesting to sort of keep in mind these different divisions, and understand as a user what questions are possible to get answered, and also as a developer, think about you don't necessarily want to, it might be frustrating, but you also don't necessarily want to share all the pain answering the easy questions up to the users, because that's not that interesting to them necessarily. So this is a sort of, this is my little overly simplified taxonomy, but I think this is a useful starting point for floating point triage and also for floating point empathy. So that's sort of background. This has always been true. Let's zoom in a little bit more on what's actually going on today. So what do I think about as a floating point, user and library developer both today? And the big question related to this research to FPBench is really is floating point about the bits, or is it about the reals? This is the question that I see a lot of tension around. So to sort of illustrate, let's just imagine a hypothetical situation. Imagine you're designing some new machine learning accelerator. You need to produce a bit accurate specification. What are the pain points going to be for the specification? What are the bugs that hardware designers are going to come back and haggle over? Well, there's a lot of things you have to figure out here, right? You have to get the rounding modes. Which ones? How are they controlled? You have to deal with subnormals. Probably going to flush them. You have to deal with overflow, underflow. You have to, if your component can add somewhere in there, you're probably going to have to answer this question. What about NANDs? Do we flush the payloads? Do we transfer them through? What about the sign? There's all of these little things. If we want to be compliant with IEEE 754, we'll have to deal with the flags and exceptions, right? And there's a whole interesting bit of haggling over whether or not those are even worth the cost of supporting. And I think we've seen some direct evidence that they are. So this is more complexity for any sort of spec. And what's interesting here is that these are all questions about bits, essentially. We haven't said anything about, actual math, what this thing is trying to compute. And sure, we can stick that down here at the bottom of the spec, but this is probably not a question that's going to consume a lot of engineering time. It's probably, it does some sequence of atomics. Maybe there's something interesting like block normalization going on. But a lot of these analyses, you run the machine learning model and you see if it works. There isn't a lot of hammering on the sort of spec to get the bits right that will consume your time as a spec author day to day fixing bugs. And so this numerical accuracy thing just gets lost, right? But in a sense, this is what we actually want to reason about. And so this sort of leads me to formulate Murphy's law for floating point specifications, right? If it can possibly be about the bits, it will be. If there's any possible way for people to be worried or confused or have a question about what bits are supposed to come out of some function or some component, they will come and ask you this question and you will have to spend your time answering it. Only once that's completely sorted out and nobody's worried about it anymore, can we actually start to reason about interesting stuff like the reals. And so, one thing that sort of pops in my head here is this quote from Alistair Reid. He's another researcher, not a floating point, but he did ARM specifications. But so his quote that I'll reproduce is, if someone has to ask a question, that's a bug in the spec, right? Until we reach this point with the bits, we won't actually be able to get to do the sort of fun mathematical reasoning. So where does that lead us? I mean, how do we, I'm sort of, saying we want to move towards this more, don't worry about the bits, think about the reals. How are we going to get there? And really, this is, I think, a question about the future of FEbench as a whole. What do I think has to happen for FEbench to be successful in my mind? And there's sort of two main points here, right? I want to be able to specify the bits easily. I'm a library builder. I care about the bits. I will always care about the bits. But I want to be able to finish that off, well enough that users aren't worried and they have the luxury of actually thinking about numerical things in the way that makes sense, worrying about accuracy instead of wondering whether or not, nan has a positive or the sign of nan is 1 or 0, because who cares? That shouldn't be an issue that consumes our time. And I do really think that we stand at a turning point here. Obviously there's a lot of interest in building accelerators for performance reasons and so on. But I also think that, we're sort of at a turning point in terms of the specification, right? IEEE 754 has gotten us a long way, but IEEE 754 and IEEE 754 is good for understanding the bits, but the problem is that it pushes the bits to the front, right? I think that the difference with a standard like FPCore, which I sort of want to, focus on as maybe not the replacement, but maybe the sort of, the next step, right? The way to specify the bits for all number systems. And importantly, a way to specify the bits so that users aren't hit in the face with them. So that developers can specify what they want and users can think about what they want without having to have that sort of, unnecessary, oh, I'm going to tell you about the importance of the guard bits so that subtractions are accurate. Like, no, subtractions should just be accurate. We don't have to worry about the implementation. We should think about numerics. So, what's the sort of call to action here? What's the point of this presentation? I do want to, I think, make a stand, and this is, this is not just open source anymore. This is being used in Intel. This is being used in, in a production environment. It has real support. It will have enduring, enduring development. I want to standardize FPCore as, the way to write all bit accurate specifications for numerical things as broadly as possible, not just IEEE 754 bits, any bits you like. And hopefully that's the sort of the main interface to solve this problem of specifications and take that pain away. I think there's also some very interesting open questions for, for programming languages. How should we write programs if we have this more numerical reasoning? I've dived into this a tiny bit with my work on syncing point in the past, but really this is wide open. I have no idea what to do. And I think there's also an interesting question for education, right? I do not believe that floating point should be like, oh, there's some bits, IEEE 754, 32 or 64 bits, take your pick. Like that's not the core idea. The core idea is about, math. It's about building this numerical tower. Like computers can do integers, they can do unbounded integers, right? You can build all this stuff up mathematically without having to resort to saying, oh, there's a bias and an exponent and a mantissa and all this scary terminology and all this confusing stuff with nans. Like that's secondary. Implementers can deal with that. Students and programmers should have the luxury of thinking about what they actually care about, which is doing real arithmetic. So just my musings. Thanks for your time. Thanks for an excellent FPTalks session this workshop. So hope you all enjoyed, and I can take questions, but I also think we're out of time. So
any quick questions for Bill on this view of splitting, thinking about bits and reals, and dropping in a spec that makes it easy to move from one to the other? Kind of a big vision.
We solved it. We did it.
So Bill, what do you think of Boehm's proposal for API for the real numbers?
Constructive reals? Yeah. So this is a super, this is a super interesting piece. And this is, if you want to dive into the details, Zach also likes this idea of teaching a numbers course, which is very foundational. And this is one of the sort of stages in the numerical tower. I think that having that be a standardized idea, this idea of, oh, I'll just have an API to go and compute some real quantity to however much precision I want, right? This is a super useful component. And like from a specification level, this is wonderful because now you can, if people say things like, oh, I compute this in reals and then round, like you can do that. It's not going to be fast, but it doesn't take, you don't have to like download a ton of special software. If somebody knows about the API, you can just get it from Python or whatever. So on the one hand, that's beautiful. On the other hand, I don't think that will ever replace, true finite precision, right? There's cases where you just need performance. And from a specification point of view, like the world I want to live in is a world where we have standard ways of reasoning, which allow us to interact with both kinds of numbers coherently, right? We can, when we need precision, we can say compute with high precision. When we don't, we can say we don't, compute quickly. And we can say things like, do I have enough precision? Is my accuracy good enough? Instead of, and then maybe even have compilers and other tools that will help us, solve those questions for us, or at least give us feedback so that we can sort of explore the space and see what happens. And I think that, like, if you're constantly haggling over, did I get the flags right? You're never going to actually think about those deeper questions. But yeah, I mean, that is part of it. And my vision is broader, right? I want a framework where both accurate and inaccurate computation, can sort of be described in familiar, useful terms, so that we can compute accurately where we need to, and we can demonstrate that low accuracy is good enough where performance is critical.
Okay, friends, on that